Hello students, today I am going to present the reactions of aldehydes and ketones. Now I am going to deal with Baeyer-Villiger oxidation. You know that the aldehydes and ketones are carbonyl compounds. They are compounds in which tetravalent carbon is bonded to divalent oxygen through double bond, and one of the valency is fulfilled by an alkyl group. The fourth valency may be an alkyl group or a hydrogen. Suppose if the fourth valency is a hydrogen, then we call them aldehydes, and if the fourth valency is another alkyl group or the same alkyl group, then we call them ketones. There is a situation when both R1 and R2 flanked by the CO group, flanked to the CO group are equal and hydrogens, then we call it a formaldehyde. It is the first member of the homologous series. You know, when R1 and R2 are both methyl groups, then we call the compound acetone. Now you also have aryl aldehydes and ketones. A aryl aldehyde has a benzene nucleus or a benzene-like nucleus attached to the carbonyl carbon. So this is when there is a benzene, that is a phenyl attached to the COH group, we call it as benzaldehyde. And when two benzene nuclei are attached to the carbonyl group, then we call it as benzophenone. So these two represent aryl aldehydes and ketones. Now there is one more thing. When there is a cyclic compound which is having a keto group, then it is called an alicyclic ketone, and its name in the example shown to you is cyclohexanone. There is one more to this. Suppose if the ketone is having an alkyl group and also an aryl group, then we call it as an aryl alkyl ketones, and they are very important group of compounds. The Baeyer-Villiger oxidation that I am going to deal today will be dealing with these aryl alkyl ketones. Now the aryl alkyl ketone shown to you in the picture is acetophenone. Now what and how does aldehydes and ketones react? Carbonyl compounds primarily undergo nucleophilic addition reactions. You all know this, but this nucleophilic addition may be either direct attack of the nucleophile or through enolate attack. And now there are plate attack. Now both of them are represented by an example of ammonia attacking the carbon, the electron deficient carbon. This is an example of direct attack, and another example is the enolate attack where the aldol is formed. It is shown in the second example. Now I am going to deal Baeyer-Villiger oxidation. Whenever we try to learn a new reaction, we try to go from known to unknown. Any learning should be from known to unknown, and I am quite sure that you are all very familiar with Aldol reaction. Baeyer-Villiger is relatively an unknown reaction to undergraduate students. That is why our journey would be from Aldol reaction to Baeyer-Villiger reaction. I know that undergraduate students are very much familiar with Aldol reaction, which they are exposed to at a +2 level. Hence Aldol reaction is taken as a lead compound or lead reaction. You can see the stabilization of the nucleophile through keto-enol tautomerism. You can see the keto form on the left hand side of the representation of the equation, and on the right side there is an enolate ion. It is an enolate ion. It is the enol form of the acetone acetaldehyde that I am going to deal. Now when you go further, you know that Aldol reaction is the addition of enolate form of the nucleophile on carbonyl carbon of an aldehyde or a ketone, whereas Baeyer-Villiger is the addition of nucleophile on the carbonyl carbon of a ketone. Now, what is the difference between the Baeyer-Villiger oxidation that we are going to learn today and aldol reaction? In aldol, no separate reagent is required. You know that aldol is a coupling reaction where nucleophile is generated from a molecule of the same carbonyl compound, which is the substrate. In Baeyer-Villiger, a separate reagent like a peroxide, also called as a peracid or peroxide catalyst, is required. Now, in Baeyer-Villiger, the reagents that we use are metachloroperoxybenzoic acid, which is called as MCPBA, and TFPAA, which is trifluoroperoxyestic acid. I am going to depict MCPBA by replacing chlorophenyl moiety with R for simplicity. Now, what is Baeyer-Villiger oxidation? It is a reaction in which a ketone is oxidized with a peroxy acid to an ester. You can see the ketone that is given as containing two alkyl groups, one of which is a bulkier alkyl group, and you can see the bulkier alkyl group migrating to the oxygen side. Now, Baeyer-Villiger oxidation can also be a conversion of a cyclic ketone into a lactone. Whenever there is a cycloketone available, when it becomes an ester and it is since it is a cyclic, you call it as a lactone, and here the example given is a delta lactone, alpha, beta, gamma and delta. Now, the mechanism of Baeyer-Villiger oxidation starts with ionization of the peroxy acid. You know that the peroxy acid gives an anion of the acid. Now, the proton released in the ionization attacks the oxygen and makes the carbonyl carbon much more electron deficient. This means the carbonyl carbon has become more electrophilic. Attack of the nucleophile, that is anion of the peroxy acid attacking the electron deficient carbonyl carbon, giving rise to an intermediate which is known as Kriege intermediate. Kriege is a scientist, and this intermediate has been isolated by Kriege, hence it is given the name Kriege intermediate. Migration of the bulky group takes place in the next step. Now, the migration will be to the peroxide oxygen with the simultaneous leaving of the acid. This happens in a concerted fashion, that is bond breaking and bond making will happen simultaneously, and after the elimination of the proton you get the product. This is the Baeyer-Villiger oxidation. Now, regarding the migration of the alkyl group, you will see that the bulkier group will migrate first. This is same as saying substituted alkyl groups will migrate first. This is also same as saying the most electron rich alkyl group will migrate first. There is an order for the migration ability of alkyl groups. It is tertiary greater than cyclohexyl, greater than secondary, greater than benzyl, phenyl, and primary, and last is hydrogen. Hence, you can safely say that aldehydes will not undergo Baeyer-Villiger oxidation. The necessary and sufficient condition for the reaction to occur is that the migrating group and the peroxy bond, that is O bond, should be trans-periplanar or anti-periplanar to each other. Now, what is this trans-periplanar? Trans means opposite, peri means nearly, approximately, and planar means in the plane. So, when you say trans-periplanar, it indicates two groups lying in plane but opposite to each other. this condition should be met for the Baeyer-Villiger oxidation to take place. That is, the migration of alkyl group should be a compulsory thing for Baeyer-Villiger oxidation. Now, let us see all the stages of the mechanism. In the first stage, ionization has taken place. In the second place, attack of the generated proton on the oxygen atom, and in the third stage, the nucleophile attacks the electron deficient carbon. In the fourth stage, Craigie intermediate will self-organize in a concerted fashion to leave out the acid moiety, and with the simultaneous migration of the alkyl group, bulkier alkyl group. And in the last stage, the proton is eliminated to give the product. Now, the Baeyer and Villiger oxidation was proposed, was actually made possible by Baeyer and Villiger, two famous scientists. You know that Adolf von Baeyer was one of the most illustrious organic chemists in history. He contributed to the commercialization of synthetic indigo. Bayer's other claim of fame is his synthesis of barbituric acid. It was named after his girlfriend Barbara. It sounds great, but it is the reality. Now, Bayer's real joy was in his laboratory, and he deplored any outside work that took him away from his bench. In chemistry, bench means a chemist works on on his table, having his chemicals and all utensils and apparatus. That is called workbench of a chemist. And for Baeyer, it is everything. He used to spend most of his life at the workbench, and he has served for almost 50 years before he was awarded Nobel Prize in 1905 at the age of 70. Now, his student Victor Villiger was born in Switzerland, Munich, to work with Adolf. This Baeyer-Villiger oxidation, which was a very famous reaction, and it was a very old reaction. It was the publication was done in 1899 in an European journal, and it was very famous reaction at the time. Even today also, you can see the Baeyer-Villiger oxidation being taking place in many natural processes and in the synthesis of natural products through artificial means. So, that is the importance of Baeyer-Villiger oxidation. I hope students, you are very clear with two reactions, the one which you already know, which is Aldol reaction, and the second one which you were taught today, that is Baeyer-Villiger oxidation. I hope you are very clear. The second subtopic will be the reactions of aldehydes and ketones and its reduction. Now, I am going to deal with Clemmensen and Wolff-Kishner reductions. What is a reduction reaction? Reduction of a compound, an aldehyde or a ketone, is the de-oxygenation of carbonyl oxygen followed by hydrogenation in presence of a reducing agent. Now, whenever a carbonyl group is oxidized, you get a methylene group, CH2. You can see this in the pictorial representation. Now, today's class, I have divided the reductions into two, Clemmensen and Wolff-Kishner reduction. Although Wolff-Kishner reduction was came into limelight much earlier than the earlier one, but I am going to present the first reduction reaction as Clemmensen reduction. The conversion of carbonyl compounds into hydrocarbons in presence of zinc amalgam and hydrochloric acid is the Clemmensen reduction. So, zinc amalgam, what is this zinc amalgam? When you mix or combine, when you mix zinc and mercury, you call it as amalgam. Mercury gives a solution, it gives a homogeneous solution. Now, when this is used along with the hydrochloric acid, you get the required conditions, that is hydrogen is generated and you get the methylene group where the acetophenone, that is a ketone giving a hydrocarbon. Now, why you are using mercury? What is the role of mercury? Zinc dissolves in mercury forming zinc solution. This is the catalytic surface for the reduction reaction. So, zinc amalgam will provide the catalytic surface for the zinc to be spread uniformly. Zinc atoms will be uniformly spread in the amalgamated solution. Under normal conditions, zinc releases molecular hydrogen to the surroundings, but the amalgam ensures that the nascent hydrogen is entrapped in between the zinc atoms. You can see the entrapped hydrogen in between the zinc on the surface of the zinc amalgam solution. Now, the carbonyl oxygen is removed through contact with the zinc atoms as the zinc oxide, and the entrapped nascent hydrogen on contact with unsaturated carbon hydrogenates it. You can see this in the pictorial representation. Here the carbonyl oxygen is being interacted with the zinc and it is being removed as a zinc oxide. In the second pictorial representation, you can see zinc and HCl giving rise to nascent hydrogen which is entrapped between two zinc atoms. This is only for pictorial representation for better understanding to the students. This does not present the actual scenario. Now, this carbene and the zinc, this is called Zinc-Carbenoid Mechanism, and this will see that the hydrogen interacts with the double bond and generates a methylene group. There is one more mechanism, it is called radical anion mechanism. Initially, a single electron is transferred from the catalyst or catalytic surface onto the carbonyl oxygen, producing a radical anion. At the expense of the pi bond, the pi bond is broken and you get a radical anion, because when electron is abstracted by the oxygen and the oxygen becomes a negative charged ion and the radical is there at the carbon, that is an electron is there at the carbon. So, it is a radical anion. Now, in the second stage, the proton is added along with an electron, which is effectively the addition of a nascent hydrogen. When I say nascent, it indicates newly born. So, the zinc and HCl interact and produce a hydrogen, and there is an electron also trapped on the surface of the catalyst, and you get a radical anion. After that, you are getting the hydrogen attached to the carbon. In the next stage, carbonyl oxygen leaves and chlorine is added simultaneously, that is in an SN2 fashion. That is a concerted mechanism. Now, you got a chlorine attached to the carbon. In the next step, an electron is will make that chlorine is and the chlorine bond, the CCl bond is broken, and you get a free radical once again. And this free radical will interact with the nascent hydrogen, giving completing the transfer. So, I am very sorry to say that the arrowhead should point towards the product, that is towards the right side. I hope you can understand that. Now, reduction of acetophenone to the corresponding hydrocarbon. I want to give an example of acetophenone being reduced to a hydrocarbon. You can see in the first step electron abstraction, followed by radical anion generation, followed by hydrogen atom abstraction, followed by SN2 mechanism, followed by chlorine detachment through bond fission, homolytic bond fission, and then in the final stage again hydrogen abstract leading to the product which is an ethyl benzene. So, in effect an acetophenone, a ketone is being transferred into an ethyl benzene, an alkyl benzene. Now, limitations of Clemmensen reduction. Reduction takes place in strong acidic medium, hence the compounds that are unstable in acidic medium cannot be reduced by Clemmensen method. Aryl aldehydes and aryl alkyl ketones are easily reduced, whereas aliphatic carbonyl compounds require anhydrous conditions. Now, let us remember Clemmensen, because he has done immense service by giving us the very important reaction where hydrogen is added to the CO group, giving rise to methylene. So, Clemmensen was born in Denmark. He received his MS degree from the Royal Polytechnic Institution in Copenhagen. In 1900, Clemmensen immigrated to the United States. Almost all the famous scientists of those times used to immigrate to America. He worked at Davies and Company, which is now called as Pfizer, and where he discovered the reduction of these compounds with amalgamated zinc. Now, you know that it is a very famous reaction, and several hundreds and thousands and millions of compounds were reduced. And he has presented his work through his paper in a journal in 1837. It was a very older reaction. Now, let us come to Wolff-Kishner reduction, conversion of the carbonyl compounds into hydrocarbons by refluxing with hydrazine in basic medium will also give hydrocarbons, just like in the earlier reaction. So, here also I am taking acetophenone, and the medium is a hydrazine. You can see the hydrazine in potassium hydroxide. It is a basic medium, it is an alkaline medium. The earlier one is an acidic medium. And now, Wolff-Kishner mechanism is in the initial step hydrazine adds onto a carbonyl group to give a condensation intermediate named hydrazone. You can see hydrazone. This is a condensation because water is lost in the process. Now, if you see the whole mechanism, the carbonyl compound is first being attacked by the nucleophile. It is a direct nucleophile attack reaction where water is lost and hydrazone is formed. In the next step, proton is removed, and you get an anion on the nitrogen. This further one more proton is abstracted, giving a diimide. The first one is an imide, the second one is a diimide, and the imide loses nitrogen, giving a carbanion. This carbanion will interact with the water molecule and abstracts a proton, giving to the product which is an hydrocarbon, as you can see. Now, what are the limitations of Wolff-Kishner reduction? It is also a reduction which is taking place in a strong medium. Of course, it differs from the earlier one that it is basic medium, and the earlier one is an acidic medium. Hence, the carbonyl compound that are unstable in basic medium cannot be reduced by Wolff-Kishner reduction. Aryl aldehydes and aryl alkyl ketones are easily reduced, whereas aliphatic carbonyl compounds require anhydrous conditions. Now, these two works were actually published in two separate journals. The first one was done in 1911 and the second one was done in 1912. I hope you are very clear about the reactions Clemmensen and Wolff-Kishner. Now when you are given a ketone, you know the conditions and how they are converted into a methyl compound. Thank you. My last subtopic will be analysis of aldehydes and ketones. You know what is analysis. Let us see what is analysis. Analysis is detailed examination. Analysis involves identification, that is both qualitative and quantitative. You call quantitative analysis as quantification, where you can get the amount. For quantification, you can say the example of volumetric analysis, where you exactly know how much you are getting as how much amount you are getting. This presentation of course will deal with the identification of aldehydes and ketones exclusively, and it does not deal with the quantification. Now what is qualitative analysis? For a chemist, it is by means of chemicals, chemical reagents. Of course nowadays spectral study is also being used, but in this presentation I am going to limit my discussion to chemical means of identification. Of course there is one more means of identification, which is called physical means, that is melting point, then dipole moment, and all these things come into physical means of analysis. And now I am going to deal with the Fehling's reagent, BENEDICT'S reagent, TOLLEN'S reagent, and 2,4-DNP, which is a dinitrophenyl hydrazine. What is Fehling's reagent? Fehling's reagent is a combination of two solutions, namely Fehling A and Fehling B. Fehling A is copper sulfate solution. Fehling B is alkaline solution of sodium potassium tartarate. Now what is sodium potassium tartarate? Sodium potassium tartrate is a crystalline solid. It is called as a Rochelle salt. It is very famous, and it is a piezoelectric material. The physics people knows it very well, and they use in resonators and vibrators. Now Rochelle salt is a sodium potassium tartrate, and it has water of crystallization. It is a tetrahydrate. Now dissolution of solid crystals of sodium potassium tartrate in alkaline solution, that is either potassium hydroxide in water or sodium hydroxide in water, will give Fehling B solution. And you can see that this tartrate, sodium potassium tartrate, is a bidentate ligand. It has two donor atoms. And now adding Fehling B and Fehling A solutions result in the formation of a complex with a cupric complex with a sodium potassium tartrate salt. You can see this when blue copper sulfate is added with sodium potassium tartrate, you get a cupric complex, and you can see this is a square planar complex. You will be more clearly seeing that in the next slide. See, copper at the middle, it is a cupric ion +2 charge will be there over it. Of course, it is not shown because it is a complex, and there are 4 coordinate covalent bonds with oxygens. So, each bidentate ligand, that is sodium potassium tartrate, is giving 2 bonds with the copper. Hence, there are total of 4 bonds, and you got a square planar complex. Now, Fehling A and Fehling B are combined just before adding the sample. This is called in situ, means in the workbench you add both of them. But why don't you add earlier? It is because if you add both of them before the reaction, then there is a chance that cupric hydroxide is formed, and it is a PPT, it is a precipitate, and it may spoil or it may intervene with the identification of the aldehyde or ketone. So, complexation of cupric ion with sodium potassium tartrate is kinetically favored over cupric hydroxide. See, what is kinetically favored? We can say, just imagine a running race where 2 contestants are running. Suppose contestant A, that is copper sulfate combining with Rochelle salt, has reached the destination first. You say that it is the winner of the run. So, when I say kinetically favored, I mean to say that it is formed first. It has won the race with cupric hydroxide. So, the formation of the cupric hydroxide will take longer time. And now, when the sample is introduced into the Fehling solution containing Fehling A and Fehling B, which is blue colored, and it is warmed over a water bath for a few minutes, you get a red colored precipitate. Sometimes it may be a reddish brown. It depends on the aldehyde or ketone that is used. So, generally I am depicting this with a red coloration. The colored precipitate indicates the presence of aldehyde group in the given sample. And now, what is the chemistry behind the Fehling test? You can see an aldehyde reacting with a cupric complex in presence of alkaline medium, that is 5 hydroxyl ions are depicted here. It is only for stoichiometric purpose, and you get a carboxyl acid, the anion of the acid, and a red precipitate which is cupric ion. So, what is happening effectively is that the O is being attached to the C double bond O group. Hence, the formation of an acid is possible. In this case, it is an acetate, and the reagent which is added has been released in the final stage. Now, alpha hydroxy ketones also respond, because CC bond cleavage is possible due to the presence of OH group, hydroxyl group at alpha position. So, when Fehling reagent is added to the alpha hydroxy ketone, you get a red precipitate. Now, what are the limitations of Fehling test? Fehling reagent is a mild oxidant. It cannot oxidize ketones to carboxylic acids. Hence, ketones do not respond to Fehling's test. But alpha hydroxy ketones respond to Fehling's test, because CC bond cleavage is possible in this case. Limitations of Fehling test, some more limitations are there. Ketones does not form carboxylic acids with same number of carbon atoms. There is CC bond cleavage issue, because Fehling solution is a mild oxidant, as already has been told to you. So, Fehling reagent will not respond to a ketone. Now, strongly alkaline, there are few more limitations. Strongly alkaline solution of Fehling solution may destabilize some susceptible carbonyl compounds. Hence, milder alkaline conditions are employed, replacing sodium hydroxide or potassium hydroxide with a sodium carbonate. This is a milder base. The modified reagent is called BENEDICT'S reagent, and I am going to deal with the BENEDICT'S reagent. It is an alkaline solution of copper sulfate complexed with citrate, and the alkali or the base used is sodium carbonate. Citrate is a tridentate ligand. Tartrate, remember, it is a bidentate ligand. Now it is a tridentate ligand. Hence, the copper complex formed will be hexavalent, giving an octahedral complex. Now, I am not showing you the complex exactly, but I am showing two citrate moieties entrapping copper, cupric ion. So, this is the main aim. Cupric ion is being protected without the formation of the cupric hydroxide, which is a PPT. So, that means a precipitate. Now, the next one is, you can see this cupric citrate complex is also a blue colored complex, and when you add the aldehyde sample, ketones will not respond to this test also. So, when you add the sample and warm it for few minutes or a water bath, you get a red color precipitate, which is the formation of a cupric oxide. So, Benedict's reagent is a milder oxidant. It cannot oxidize ketones to carboxylic acid similar as Fehling's reagent. Hence, ketones do not respond to the test. Alkalines, my next reagent would be TOLLEN'S reagent. It is an alkaline solution of ammonical silver nitrate. It is prepared by adding silver nitrate to sodium hydroxide, and you get a precipitate when you add a silver nitrate to sodium hydroxide. This is due to the formation of a AgOH. You dissolve this by adding excess ammonia solution, which is NH3. The dissolution is due to complexation. You get an amine complex of the silver, a silver complex of the amine, diamine silver. Silver ions present in the complex oxidizes aldehyde to the carboxylic acid, and itself getting reduced to silver. You know, metallic silver has a luster, you know that. Hence, in the test tube you can see the lustrous silver atoms attached to the test tube. The metallic silver is seen as a silver mirror on the walls of the test tube. See, this picture depicts metallic silver. The first left hand side test tube depicts metallic silver, whereas the other sample where ketone has been used, this is not responding to the TOLLEN'S reagent test. Now, what is the chemistry behind TOLLEN'S reagent test? It is similar as Fehling's and BENEDICT'S. The only difference is the reagent and the generation of ammonia, and also silver, which is a metal, and it has, as already seen, it is lustrous. So, you got the same carboxylate ion, which is acetate here. And now, let us see one more reagent, which is a 2,4-DNP. DNP is dinitrophenyl hydrazine. This reacts with both aldehydes and ketones. Unlike this earlier reagents, 2,4-DNP reacts with both aldehydes and ketones to give the corresponding hydrogens. Carbonyl derivatives of 2,4-DNP reagent are crystalline solids with a definite or specific melting points. And you know that melting point is a very important indicator of the purity of a compound. It is unique for a particular compound. So, these hydrogens are taken and their melting points are studied to understand whether the given one is an aldehyde or a ketone, and even if it is aldehyde or ketone, you can know the exact homologous, the compound of the homologous series. So, this is in effect the overall reactions of aldehydes and ketones, and my dear students, I hope you have now an idea of Baeyer-Villiger oxidation, some reduction reactions and everything. Thank you very much for giving me this opportunity.